Blue means it's shifted from red to blue. And that happens if you're approaching at a speed significant compared to the speed of light. Was that the question? And this is the energy of a particle if they're really, really relativistic. They're extremely relativistic, because then E naught squared is small. So, a lot going on. What else? Anything? So I got like one more thing to talk about in terms of fission. I'm going to talk about fusion, and I'll be done with reactions. And I'll probably wave my hands a little more than usual about fusion, because then we want to get into particles and things like that. Did I bring those notes?
And the test is due next Thursday or Friday?
Whatever. I mean, it's nothing to me, right? Ultimately, your grades are not due until the Monday after finals. But every day you don't turn it in is a day you don't have available to other things. So, I mean, I'm not trying to be coy, or I'm not trying to be argumentative.
No, I understand.
I'm just saying it does not affect me hardly at all. The longer you keep it on your desk, the longer it hangs over you, and the longer it interferes with everything else that you're trying to do.
Will that include the fission we're going over today?
It actually includes the fission stuff, includes fusion. So the last question is about fusion.
Okay.
So it's basically about all of the section that would normally have been finished last Tuesday, if things went exactly precisely according to plan. So I'll go a little bit longer, and then we'll start the other. But this is on reactions and decay processes. Mostly from the notes, but I've been making references to the different parts of the textbook as we go. So hopefully you can find those things. You can always come and talk to me, right? I know that you don't want to, apparently, but you can always talk to me about this. I might have to go to my office, because I think I did not bring the next set of notes. I've got all the reaction stuff here, but I don't have the particle stuff here. Depends how far I get. You guys stall me enough, then it won't happen. So, we've talked about, I'm just going to write, that was the reaction we've been talking about, and the problem, the one in there talks about essentially the same reaction, except it's 233, and I think instead of krypton, it's xenon. In fact, I think it's two other products. I had some difficulty finding those. The main thing that I had difficulty with was how many neutrons come out of the various reaction processes. But we talked about the potential advantage of that. The advantage of the extra neutrons is that you could induce even more reactions than you started with. If you get, on average, one extra reaction out of this, if you have a net one reaction, then that's sort of keeping it just barely going, and that had to do with the likelihood of losing one and so on. We talked in general terms about losing it out the sides, quote unquote. And so that's what I'm going to talk about today, is how to think about what the odds are of losing one of those. And so the way to think about it, a way I find useful to think about it, I have a... Yes.
Today's that day.
I shouldn't have been using that one anyway. Yes, today is a good day. I have an impactor. This is the particle that's going to collide with something, and it's moving along. So as it moves along, it carves out this cylinder. So it carves out of a cylinder of the cross section for whatever this is times, I'm using my notes, I'm using a lowercase l. That's pretty common. remember we interpreted that sigma as an area. If these were hard shell scattering, then it would really be the surface area, but we also know that actual cross sections typically, at least by definition, have almost nothing to do with the physical size of the object. They're a ratio of events per particle per unit area, flux. So it winds up having a unit of area. Sometimes we get lucky and it is in fact the size of the object, the area. Other times nothing to do. An example I read about the other day, the neutron scattering cross section for a proton is 10 times bigger than the scattering cross section of a deuteron. So think about what I just said. Scattering cross section for a proton is 10 times bigger than the scattering cross section for a deuteron. Can we interpret that in terms of the size of the things doing the scattering? And this is Lanyard. This is extra knowledge. You don't have to. This won't be on a test. This is Lanyard. You didn't pay for this.
We know that a deuteron is a lot bigger than a proton.
A deuteron is a proton and a neutron.
So it's twice as big.
Twice as big. Twice the area, right?
Mm-hmm.
Not like twice the radius. It's twice the area. And what did I say the scattering cross-section comparison was?
So the proton was 10 times bigger. And that's when you shoot a neutron at them?
This is neutron scattering. But even if you don't even know it's doing the scattering. The question is, can you interpret that scattering cross-section as having to do with the physical size of the thing doing the scattering? Not even close, right? Absolutely no way to interpret that in terms of the size of the object. It's definitely something different, right? Whatever it is, it's different. So, and that's what you need to do, right? That's the job. The reason we know stuff about that is we bang things into them. We interpret the scattering cross-section. We figure out how to model the scattering cross-section to tell us what's going on inside there. So, having said that, that's what I'm going to do. Because I'm going to say that this scattering cross-section times this length, and I'm going to compare that to the volume per scattering particle. Every single particle in there has a certain volume assigned to it, and it's that. That's the volume each one. And then I'm going to say that if I put those two equal to each other, I'm going to call that length of this tube the mean free path. About how far can it go before it bangs into something? And about as far as it can go before it bangs into something is when the volume it sweeps out is about the same as that volume there. I looked around for some good descriptions of it, or like a cute video or something like that, and I just didn't find anything that I thought was more useful than that. So think about that. I'll keep looking. If you guys find something, let me know. But that means I can now estimate what those are, because all I need to know is scattering cross-section, number, density of particles. And I'm just going to write down what that turns out to be and see if I can. L then V over N sigma. N is the mass of each particle divided by the total mass of all the particles. Nope, other way. Total mass of my sample divided by the mass of each particle. So if I'm talking about a neutron slamming into a uranium to start this reaction going, then this would be the mass of each uranium nucleus. That would be the total mass of my sample. That would be sigma. That would be, and that's the scattering cross section. I'm going to call that the physical size, right? in spite of everything I just said. V is just the volume of my stuff, whatever it may be. So the mass of each particle divided by mass per unit volume is the density, and that's scattering cross-section. Then if I just put in numbers, M is 235. Mass of a nucleon, density, I looked that up, 19,000 kilograms per cubic meter. Pi onto 1.07 times 2/3. What did I do? Mass of a nucleus is 235, that's the mass number of mass of a nucleon. Density, I Googled that. Mass per unit volume of whatever this is. Sigma, I wrote as pi r squared. Nope. Yes, pi r squared. I got 0.151 meters when I do that calculation. To get the mass of that sample, let me go back. What is that telling me? I got a spherical piece of uranium. If it were that big, a neutron generated in the center would just barely react with something, no matter which way it went. If it was generated over here, there's a reasonable chance it would leave before it did anything. If it went the other way, it would hit something. So I said, well, let's say that that's about as big as you can be. If the mean free path is the same as that radius, if this radius is the mean free path, that's like the edge of whether this will continue and whether the neutrons it generates will stay in there, and it generates will stay in there, and this is obviously a completely, hopelessly oversimplistic picture. But then I said, then that's as big a piece of uranium as I need for this reaction to go. Remember, if you had, remember that nu q minus 1, if that was positive, the reaction went. If it was negative, it would die. Essentially, if the radius is this size or bigger, this is positive. If the radius is that size or smaller, this is negative. So that radius is about the edge of this reaction, either growing exponentially or dying away exponentially. In that case, I can find the mass, which is the density, which I already know, times a volume this big, I got 19,000 kilograms per cubic meter times 0.014 cubic meters, or 263 kilograms, which is around 500 pounds. Our critical is more like 0.09. So given how mind-bendingly simplistic this is, I think that's not so bad. That I was within about a factor of 2. So they talk about critical mass, that's what they mean. What mass do you need before it will go? Now, what's not here is that it's really not the mass that matters. It's whether or not these particles are big enough. You need the mean free path. So what could I do? One thing I could do is I could change, all else the same, all I need to do is then change this number or this number. I could compress that, right? I could squeeze it. If you saw Fat Man and the Little Boy, or what was the other one? Oppenheimer, they talked about building these bombs by putting a lot of explosives around it and compressing it. And they had to design an explosion that would go in instead of out, right? That was an entire, and so they had they used optics to design those explosives so that the shock wave would go in. They designed, instead of a diverging explosion, it was a converging explosion. And you basically use the idea of optics, about different wave speeds for that explosion, to compress that. To compress this number, make this smaller. Make this bigger, sorry. They compress it, they have the same mass, they put it in a smaller volume, the density goes up. They didn't do it with uranium, they did it with plutonium. But the point is that what you need is for the mean free path to be roughly the size of your sample. However you do that, and there's different ways to do that. So, any questions about any of this? That was the last thing I wanted to talk to you about fission reactions. And there's a lot of sections in there about reactor design. If you care about reactors, it's in there. Fusion. What happens if I fuse 2 iron molecules?
You lose energy.
Yeah. To make that happen, I got to put in a net energy in, right? We even know where it's got to come, where it goes to. We get a benefit from the surface term, but the Coulomb term wins. And so we've got to actually provide enough energy for that Coulomb force to get them close together. I get a little bit of it back when they make a sphere, and we get that back in the form of less surface energy compared to the volume. But it's not enough to make up for the Coulomb term. So I don't get energy if I fuse things down at the bottom. I get energy when things near the bottom break up into 2 pieces. But that changes after I get to iron. Below iron, what happens? Now I gain energy. And it's still a competition. I'm not going to go into the details of it, but it's still a competition between the various terms that give you, now you get energy when you fuse them together. One question that occurred to me, tell me what all those little strokes mean. Tell me what everything up there means.
First one is a neutron.
A neutron, he did his part. Say again? Okay, done. All right, so they're going fast. Let's go, let's keep it going.
I thought those are T's, those are pluses, right?
Those are pluses. Okay, no, that's done. It's on you. What's that?
Electron?
Boom. Let's hear it. Left the best for last.
The anti-electron neutrino?
Okay, he is up to the task. That's exactly right. That's exactly right. Because I have baryons. Let's look at the baryons. This is again more lagniappe, but we'll use this when we start talking about particle physics. Tell me the baryon number for every single one of those. That's pretty easy, because if you're a baryon, your baryon number is 1, and if you're not a baryon, your baryon number is 0. So
the neutron and proton are ones. The electron and anti-electron neutrinos are zeros.
So is the baryon number conserved? Yes. And this is the game in particle physics. We got nothing. We are pulling at every thread we can find to see what kind of patterns can we get out of this? What can we see? We know a lot now compared to where we were, but this was trying to be order out of chaos. One thing to keep in mind is that they started off like banging things together, right? You had a proton, an electron, boom, you had a proton, electron. Awesome. A little faster, right? For reasons that we talked about, you take that in a little bit faster. A little faster, a little faster, a little faster. Now you got more particles. Chemists, you don't have a problem, right? However many electrons and protons and neutrons you have at the beginning of the reaction, that's what you have at the end. You don't have to worry about extra stuff popping up. In particle physics, when they started banging these things in, eventually the energies of the collisions were bigger than half an MeV. When that happens, what happens? You can now make an electron. You got enough energy that instead of having kinetic energy, you can take some of that kinetic energy traded for particles. If you get up to a GeV, you can start making those. And if you go above there, you make stuff that nobody's ever heard of. So you start off with electrons, protons, and neutrons. Then dozens of particles. Now what? Now it's chaos again, right? Just when you thought you had it all figured out, now we got to figure it out again. And so stuff like, what is the baryon number? Is that conserved? And if so, what does it do for us? All right, let's do lepton numbers. Would be a good choice for the lepton number of a neutron.
Zeros.
That's what I would pick. I would pick 0, 2. What about a proton?
0.
What's a good lepton number for an electron?
1.
What had the lepton number of an anti-electron neutrino better be if this new weird lepton number is supposed to be conserved?
-1.
Better be -1. Or I could do this. Later on, we're going to do this. Actually, I think we did talk about that a little bit, about detecting neutrinos. We did some of this when we were, I think. I either did it in this class previously, I'm going to do it in this class later, or I've done it at one time in my life. So they're all kind of the same thing for me. What about now? Lepton numbers. I'm going to change these.
So it's not an anti-electron neutrino?
Yeah, better not be, because if I'm going to conserve this neutron, that needs to be an electron neutrino. It needs to be the antiparticle of this. You could write similar things for beta plus decays. We'll do some of these things when we start playing all these numerological games later. We talked a little bit about conservation and how more other stuff is conserved. One of the things that's conserved is energy, right? Because that's a spontaneous reaction. It takes about 15 minutes. So tell me this, why are there any neutrons in the universe? Because if you start off with the universe being electrically neutral, let's say it's all neutrons, why are there any left? What about this? What if I put the neutron and the proton together? What's the lifetime of the neutron? How long does it take for that to beta decay? It's a trick question. It doesn't beta decay as far as we know. So something happens when you keep them safe in a group. So what does that tell you about the creation of matter in the universe? If it took more than 15 minutes to make deuterons and helium-4, and if it took more than 15 minutes to do that, there wouldn't be any neutrons left. They would have all decayed to protons, and it would be a proton universe. So whatever your model of universal creation is, this step has to happen before this step. That's a constraint on your model for cosmology, your model for how the universe started. Think a little bit about why those neutrons don't decay. Think about conserving stuff and think about why you wouldn't expect those to decay. So now I'm kind of following Dunlop and Iceberg, but during that Big Bang, when all this was going on, his picture, you start off with just neutrons. Now we actually know even before that there was a step where you didn't even have that. You had one big gigantic nucleus where all the quarks are just free to move about. We're not going to go there, at least not yet. We will eventually. We'll try to. Spend a little time thinking about why the neutron is safe now. Why doesn't a deuteron? Why doesn't the neutron and the deuteron beta decay? If that happens twice, I can then do this. I can get a helium-3. Where does the 3 go? I know where I have it in my notes, but I know that I can't trust my notes anymore. Top. This supposedly has a Q of 3.3 mega electron volts. This supposedly has a Q of 4.0 mega electron volts. Now I have helium-3s in my universe. And again, you don't really have to write this down. I'm just take helium-3s. Nope. If there's time, this neutron will decay. If there's time, this neutron will decay. It changes the level of reactance. But when that process, you wind up with hydrogen. Because any neutrons will eventually decay. If they're left hanging, they will eventually decay. They'll be protons, hydrogen, helium, and radiation. If you're more careful about it, apparently you pick up a little bit of lithium at the very beginning. I don't know that reaction, but that's something you can Google and find out. But that's all you had at the very beginning. You had hydrogen, helium, and again, apparently a little bit of lithium. These are the reactions that happen once you get to the point to where you have nucleons who can then interact with each other. This is a big plasma. None of the electrons are stuck to these. You have this electromagnetic radiation. In the 351 class, very early on, this is the radiation-dominated universe. So in 351, towards the end of the class, when we talk about cosmology, we talk about this step as an early part where radiation is a really, really big deal. Not like now. Right now, radiation is nothing. Radiation is a trivial part of the energy. Right now, we're matter-dominated. And the matter is what makes it slow down and collapse back on itself, or just barely grow forever. So early on, this is less important than this. Later on, as it expands, this becomes unimportant, and you're dominated by the hydrogen and helium, a little bit of lithium. Where do you bet the rest of it comes from? That's what you get in the Big Bang.
The rest comes from stars.
Inside stars. Yeah. So our star is turning hydrogen into helium. Makes a little bit of some other elements, but mostly hydrogen into helium. The sun is a mass of incandescent gas at a temperature of millions of degrees. Turns hydrogen into helium. No, that's when it comes in. I blew it. It's a They Might Be Giant song, and it's awesome. You should probably listen to it. It will eventually start making carbon and nitrogen and oxygen. It basically does things like jam two heliums together. You got two heliums and you jam them together, you got beryllium. Take a beryllium, jam a helium onto it, you get carbon. Turns out you can't just build it one nucleon at a time. Look at the table and tell me why you can't just build them up one at a time.
Because eventually it'll reach iron and we'll stop there.
Way before we get there, we reach a choke point. My point is that you can build things with helium nuclei. Helium nuclei are incredibly stable. You saw that with we calculated the binding energy per unit nucleon, and it was like 8. It was already 8. 8 is as good as it ever gets. 8 MeV per nucleon. Helium is that, right? So it's incredibly stable for being as small as it is. So why can't you just throw on another nucleon, a helium-5? For whatever reason, it won't stay. Helium-5 just won't stay. You go from 4 all the way to 7. There's a couple of 6 isotopes, but 5, apparently A = 5 is a choke point. You just can't get past it. You gotta make a deuteron and then glom the deuteron onto it. Apparently, that's what I'm told. There's nothing I haven't found anything in the mass formula, that simple-minded mass formula, that shows you why that shouldn't happen. So it's more complicated than that, but for whatever reason. But once you have a helium and deuterons hanging around, you can you can fuse a helium with a deuteron. And what happens? What do you get when you do that? 2, 3, 4, 5, 6. That would be a version of lithium, and so on. Stars you need to get all the way up. And then, where do stars stop? Iron. Why do they stop at iron?
After that, they're not generating energy from fusion.
Yep. Now you need to give the energy. And those happen spontaneously because they release energy in the process. So you need something non-stable. You need a supernova, you need a neutron star with an earthquake on its surface or something like that. Right? You need some other mechanism that's not an equilibrium thermodynamic process where you just build things up and get energy out of it. So that's where all the rest of it comes from. So apparently the star that preceded ours went supernova, which is how we wind up with gold and lanthanum and hafnium and all the rest of it. Okay, so generally, let's think about how that energy that you can calculate from the mass formula, how that gets distributed. We kind of talked about this a little bit before, but never hurts to say it again. So I think I've talked about this as a way to write reactions. Does that look familiar? You start with X, you hit it with an A, you wind up with Y, which releases a B. So tell me how to write the, okay, you can't do that one because it splits in two. I want to do an example, but the uranium won't work in that format, so. I don't have them right here. Here's one. This one I think I wrote a while back. Beryllium-9, you hit it with an alpha particle, you get carbon-12 with a neutron at the end. Right? So you go through there and make sure that all the parts are still around. Generally speaking, here, to get the Q, their Q of the reaction, not mine, you take the mass of X plus the mass of A minus the mass of Y minus the mass of B. And then I can assume that difference in rest mass energy is distributed with the Y and B products. I'm not including any kinetic energy that A might have. Example, when you would get away with that would be like a thermal neutron. Thermal neutrons have incredibly small energy. It's a tiny fraction of an MeV, an EV. Right? They have a tiny, tiny, tiny amount of energy on this scale. And they're going 2,000 meters a second. They're going fast by our standards, but they're incredibly low energy because they're so massive. So, if this were big enough, comparable to these numbers here, then you probably have to include it. A lot of times, if this is too energetic, it won't attach. It won't lodge in. A really highly energetic neutron, if it hit a uranium, it would bounce. It wouldn't stick. It seems sort of intuitive. You know, if it's going really, really fast, it would be going too fast to stick, and only if it's going slow will it stick. So, intuitive doesn't mean true. In fact, you should almost never count on it. But that seems intuitive to me, that we seldom need to worry about any kinetic energy that A might have, even though strictly it's got to have some, otherwise how would it get there? All right, I'm also going to say that MY VY equals MB VB, what statement am I making there, and what assumption am I making? Tell me everything I'm assuming must be true to get away with what I've written. What is this statement?
The momentum of Y equals the momentum of B.
Yep, and why would that be?
Momentum is conserved.
And what does it start off as? 0, right? These momenta have to have the same magnitude and point in opposite directions if I start off with 0 momentum. What assumption am I making there when I write the kinetic energy that way?
the kinetic energy is not conserved? Or that,
I'm not counting, I'm saying A has so little kinetic energy, I'm not even gonna worry about it. It needs to be, to be of concern, it needs to be in the mega electron volt range. So I'm discounting problems where I need mega electron volts in my impact particle. So I'm definitely saying this doesn't have enough energy to worry about. I'm saying the only things moving significantly are B and Y. Their momentum balances, and I can write their kinetic energy as 1/2 mv squared. That's my hint.
so they're not moving that fast?
Yeah, they're moving sub-relativistic, right? Not this. So I can take this, solve for, what did I solve for? VB. Solve this for VB right there. I will then have something that looks like 1/2 my Vy squared. It will be that same kinetic energy. I can get this in the form of the kinetic energy of Y. This is Vy. 1/2 my Vy squared. Onto 1 plus my over mv. This is the energy that's available. So EY, the energy that particle Y will have, is whatever the reaction energy is divided by 1 plus my over mv. I can calculate EB, the same way. I could substitute for Vy here and get an expression. I'd do the same thing. I recommend that. If this is at all hinky to you, I would do that, just to see how that works. You can also, though, do Q minus EY. And if you do that, you get Q over 1 plus MB over MY, which shouldn't freak you out. The labels B and Y are completely arbitrary. So it shouldn't be weird that EY depends on MY over MB and EB depends on MB over MY. So a couple of different paths to get there. If I then calculate the ratio of those two energies, I'm going to erase this. That winds up, you're going to have some algebra, you got a common denominator, blah, blah, blah. You got to mess around. The ratio of those energies depends on the ratio of those masses. Inversely. What's your favorite do algebra software? My favorite do integrals is integralcalculator.com, and my favorite do derivatives is derivativecalculator.com. You have a favorite algebra doer? Because I don't have one.
I don't usually use them.
Yeah, so here's the thing, here's my thought process, and you can bring me around, you can try to bring me around if you want, but I liken these things, especially things like the ones I use. I use them as a tool in the same way that I use a calculator as a tool. And so I know how to do use substitutions and trig substitutions, and I get a certain amount of personal satisfaction when I do that and I get the answer. But as a scientist, I don't necessarily have time always to do that, right? In the same way that I don't use a calculator. I don't do long division to do calculations. I use a calculator, and I liken those tools are good enough now. The integralcalculator.com and derivativecalculator.com that I like are good enough that I think they can play a useful role now. They do what I used to use a table of integrals for. There's a book, it's on my shelf, right? It's a black book and I love it, and I know right where stuff is. Sometimes it's faster for me to find it in the book than to screw around online. So, but that's only because I know how to use it. Say again?
Is it Grudge? Do you know what is it?
Probably, I'd have to look at the title, but it's everything. It's even got tables of trig functions, so, which I never used, right? I'm not that old, but I'm pretty old. It is the case that when I started high school, it was just about the time they were phasing out slide rules. So I actually used the slide rule in high school. They still had slide rule competitions, so that's when I was bored. I wonder if there's an algebra doer that sort of plays the same role.
I think Mathematica could probably do it, huh? As long as you defined all of your variables first.
I feel like it would be easier to just do the algebra.
Yes, so trying to use Mathematica to do integrals and derivatives, your statement is true. But by the time I learned how to make Mathematica do it, I was better off just using my old school table of integrals. Whereas those two websites that I talked about, I think they have a low enough barrier to entry that they're worthwhile and they're useful in that regard. Same with algebra, but same with algebra. So I guess I have used some on a couple of occasions, but I don't have a good one. So anyway, that's where I'm coming from, and that's what's brewing over here. In case you want to tell your colleagues what Norwood's up to, it's perfectly okay with me. And in the same way, you're never going to be good with a calculator. You're never going to know how to use it if you don't understand what it's doing. So you need to know what a trig substitution is. Doesn't mean you have to do them for the rest of your life. So that's also my point. You're going to suck. You're not going to be able to use those tools very well if you don't know what they're doing, if you don't know what they're for. You can't walk into a tool shed and just go to town. You need training on the tools. You need to know what they're for. What did we just find out? What if MY is really, really big compared to MB?
Then the EY over EB ratio is close to 0.
Yeah, really, really small. So where's the energy go? What if MY is really, really small compared to MB?
And that ratio is huge.
Yeah. So what did we just figure out? How do we say in words what we just figured out when looking at fractions? Where does most of the energy available go?
Smaller particle.
To the least massive particle. If they're about the same, it's 50-50, but if there's one that's significantly smaller, it gets the lion's share of that energy. And when you're building stuff, you have to worry about it, but we will wave our hands and consider two deuterons go to helium-3 plus a neutron. Where's the energy?
The neutron.
Neutron. You don't have to think about it much, right? It's ratio 3 to 1. Helium-3 plus a deuteron goes to helium-4 plus a neutron. Where's the energy?
Neutron.
So, still the neutron. And so if you're going to build a reactor, we started off talking about the Big Bang, but if you're going to build a fusion reactor, you got to figure out, how do I get energy from neutrons? How do they want to do it? Boil water.
Yeah.
The same way they did 500 years ago. Boiling water. So you would think. I can't be the first person to think about that. So there must be some good reason that there's no way to get the energy out of the neutrons except by boiling water and
That
turning
might
the
just be
turbine.
our best at the moment.
And that's the downside, right? If all you, this is just a different way of boiling water. Let's not think about it beyond, let's boil the water. I got a bad feeling that's a big part of what it is. That's what we have. So just work with what we have instead of, this is pretty different than burning coal, kind of different. Maybe there's a different way to do it. you're trying to
It's
tell.
like the saying, if all you have is a hammer, everything's a nail.
Everything's a nail, that's exactly right, and I got a bad feeling, but anyway. It is considerably outside my area of expertise, so I shouldn't be judgy about it. All right, I'm gonna erase all this. Both textbooks go through what's called the proton-proton cycle. If you Google it, like I said on the test, it's the proton-proton branch 1 cycle, which is what they're talking about. There are other branches. That's the only one that I'm holding you responsible for. The net effect of all those reactions, so I wrote them all down. And if there was a proton on one side and a proton on the other side, I crossed them off. Because what that's telling you is that I have a reactant in one reaction, a product in one reaction that is a reactant in the other. You kind of saw that in those that I just erased. I'm gonna write down a couple of this is what I already wrote down, so you don't have to write this again. Later on, there was a hydrogen 3 plus a deuteron that goes to helium 4. And so what I'm saying is that if you write down all those PP1 reactions, you might have a deuteron as a product in one reaction, it's a reactant in another. And so what I did is I went through and I just crossed those off. Right? If it was not a net product of the reaction, if it was produced and used, when you get done, you wind up with 4 protons going to a helium 4. Is that the right place? Because it's in my notes and it's freaking me out.
As long as we know what it means, I guess it doesn't matter.
Well, yeah, but this is hard enough as it is, so I should at least be making it easier and not harder. Right? That's what you get? Am I conserving anything? Go through the conservation laws. Yeah, I'm conserving baryon number, right? And that's pretty much it. Well, I guess I'm conserving lepton number because I got 0 on both sides.
You're not conserving charge.
Which is kind of important. That's a big one, right? So what do I definitely need?
2 electrons.
Electron-like things. Electrons except with positive charge,
Oh, yeah.
right? Now what am I not conserving?
Lepton number.
Definitely not conserving lepton number. What else? Am I conserving energy and momentum?
Mm-mm.
You might think, but the whole point of neutrinos is they measured energy and momentum out of that, and it wasn't conserved. That was the whole start of that. No bar, because this is the electron neutrino, not the anti-electron neutrino. Because I started off electrically neutral, I've got 4 electrons here that were with the protons. Think of that as a hydrogen atom. That means I got two of those electrons are going to hang around with that helium, even if it's plasma and they're not bound. They're still gonna hang around. these two are gonna be free to roam about, and so what are they gonna do? We haven't talked about this, but maybe you happen to know what happens when an electron and a positron meet.
They die.
They leave a legacy of radiation in the frequency range called gamma rays. And it is frequently represented as two perfect little particles racing away at a certain very specific frequency, because they'll tell you that this is 1.02 mega electron volts. And that's true, that's how much energy is available there, but it's not in two very perfectly timed frequencies. It's a weird burst of radiation, lots and lots of different frequencies that cuts off at this energy in the same way that you saw with the electron energy in a beta decay. So it is more akin to a plus charge and a minus charge spiraling into each other and vanishing, who knows where, leaving all this radiation as they accelerate. It is more akin to that than vanishing and turning into two other particles called photons. So. And that's all. So, to get a feel for what that energy is, what it translates into, near Earth, sunlight has a flux, so an energy flux, I'm not going to bother writing a symbol, of 1,300, what are the units of energy? There's lots of them, and you're right to pause, but 1,300 is actually joules. And what is a flux?
Over area?
Per unit area. Per unit time. So you'll usually see that as watts per square meter. And that's near the Earth. So if I take that if I take that energy flux and multiply it by the area of a sphere out by us, the sphere that we are on a sphere around the sun. That's the area of that. So if I take the power per unit area times the area, I get watt is a unit of power, right? I have a number here that I don't believe. In my notes, I say that the energy released in that reaction is about 1 MeV. And that's not really true. It's definitely more than 10. Is that the Earth? The one I calculated the other day, I got like more like 24. So you guys are gonna have to get a calculator and start helping me. because I wanna find out how many reactions per second that is. I know how many joules per second come out. I'm gonna use the number of joules per reaction, that's gonna tell me how many reactions per second. So I need, I think the number I have somewhere is like 24 mega electron volts. Oh, I know what I did. That's for all of them. Now I know what I did. Well, this is good enough. That whole chain. And you can get it from here, right? All you gotta do is take this total energy, this mass minus that mass. And calculate that just from the mass difference, mass defect. 24 MeV per reaction. I'm going to divide that. Yeah, I did. 24 mega electron volts per reaction, and I have 3.7 times 10 to the 26 joules per second. When I do that number, I'm going to get it reactions per second. Might as well take a second and do that. Give you guys a break from listening to me. What's the first move? Cancel the joules of the MEVs. It'd be nice to work that way, huh? Basically, we need 24 MEVs in joules. I think Google would do that, actually. I mean, if you just type, convert 24 MEVs to joules.
It's 1.5 times 10 to the 14th mega electron volts. I mean,
1.5 times 10 to the minus 14, you said?
times 10 to the 14th.
Okay. I'm trying to get it as joules, so let's go with. So here,
Okay.
24 mega electron volts is 24 times 10 to the 6th times 1.6
Okay.
times 10 to the minus 19. That's E coulombs times 1 joule per coulomb, because that's a volt. So
3.8 times 10 to the minus 12 joules.
that I find believable. And that's very convenient, because that's going to cancel 3.7 over 3.8. I wind up with 10 to the 38th reactions per second. And so we get something like 2 times 10 to the 38 reactions per neutrinos per second. Every time we get our 24 MeVs, we also get 2 positrons, throws in a little bit of extra energy. Very small compared to this, because electrons are so small. But also 2 neutrinos that come flying out. And we know that they don't interact very well, because they were there all the time and we never saw them until somebody made us look for them. So they don't interact very well. Near the Earth, the flux of neutrinos is 10 to the 38th. You're probably gonna have to do this neutrinos per second over that same 4 pi times 1.5 times 10 to the 11th meters squared. If somebody wants to do that. It's 312, 40.
.5 times 10 to the 14th.
.5 times 10 to the 14th. So around 350 was 10 to the 12th. Trillion. Billion is 10 to the 9th. 10, 11, 12 would be a trillion. So 350 trillion. What is the area of your hand? Sun's so bright, and you don't have your shade, so you block it. What's the area of your hand? This is what you do for a living. Figure stuff out. You get a weird question out of no place. You first got to figure out what does this question even mean.
I think I know where it's going, I just cannot estimate sizes.
No, that's all right. Then you jump in, since you see where we're headed here. You can jump in after somebody else does their part. That's what you call collaboration.
Just pretend your hand is rectangle.
Boom. Your hand's a rectangle.
0.015 square meters.
0 point.
0.015.
How'd you get that?
I just did like my hand. I was trying to think about it in inches, and I was like, all right, if I convert that to centimeters.
Okay, I think that may be where we are. So let's do that. Let's do that. Go.
So you want
Whatever you want to do. No, let's go through the whole process. Let's do your thought process on the
okay?
board.
So maybe like
We're going to watch a physicist at work.
6 by 3 inches.
6 by 3 inches, right?
Mm. No.
What's wrong with that?
6 inches by 3 inches.
I agree with that.
Inches square.
That's going to be 18 of something.
18 inches squared.
Yeah. And I think that may be where. So now I got to multiply that by, if I want to convert it to meters, which I'm stuck with.
You wanted to get centimeters, 2.54.
2.54 centimeters per inch. So 2.5 times 18, right?
No, you gotta do
Yeah.
square centimeters.
Yep.
And that's 6.25.
This winds up being 6.25.
Mm-hmm.
Because did I do 3 times 6? 18.
2.5 times 2.5 is 6.25.
Oh, that's square. Okay, yeah, now do that times 18. Now I'm with you.
And that's 112.5. That's square centimeters.
0.0. Tell me what you had first.
I had 0.015.
And this gives us 1. So it is close to what you had. So mine is a hopeless. Mine is for a child's hand. I was like I think I'm a third of yours, a fourth of yours. So I must have been doing a child's hand. Then, if we have 3.5 times 10 to the 14th per second per meter squared times 0.011 meters squared, what do I get? And what have I calculated?
The number of neutrinos passing through your hand per second.
So 3.5 trillion. Every second. And so they're incredibly hard to detect because it seemed like we would feel that. If there was any interaction at all, clearly hardly any. Which explains how they get from the center of the sun here anyway. I mean, it takes millions of years for light to get from the center to the outside. So, if they get here, they can't possibly be interacting with anything. So, I think I talked a little bit about detecting them, but I'll talk about that a little bit more. I think we talked about this, so I'm not going to bother going over that again. I have an electron neutrino, which is what's flying out of the sun, which is what I want to detect. I have something that has neutrons in it. What's a good thing that has neutrons in it? Say it. Pretty much everything, yeah. Pretty much anything you choose, right? So you're gonna make your choice based on convenience and ease of detection. So I've got something that's gonna change a neutron to a proton. I must have gotten religion because these are all apparently right. That was the first experiment. This was set up in the home state mine. Let me write that so it's at least somewhat legible. Went down in the home state mine and went down way underground to get away from everything. So the only things you would be detecting are neutrinos from the sun. This has a 50-day half-life to decay back to chlorine-37. So if that happens, you got to be Johnny on the spot. And so you got to take out your chlorine, look for argon-37 on like a 10-ish day scale. You've got to separate argon-37 from a whole bunch of chlorine. So again, chemists, physicists know a lot of stuff, chemists make a lot of stuff. Another reaction that was the SAGE experiment in Russia, or the Gallet, sorry, it's spelled all caps. And this was in Rome. Electron neutrino plus gallium-71 goes to germanium-71 plus an electron. That's got a time constant of 16 days. So this may be easier to set up. I don't know, but you've now got to do your detection on a weekly basis. This is a liquid. This is a gas. This is a solid, this is a solid. And maybe what's the advantage of this is, even though it happens shorter. I'm sure I knew at one point, but I don't now. So they did this, did the experiment, found out they had half as many neutrinos as they expected. And they looked, right, they did all their analysis, they did everything they could to see if they were doing something wrong in their experiment. Nope. Their experiment was the same. Same Homestake and Sage and Galax, all those experiments were getting the same result. That's always a good sign, right? You don't trust just one person. So 3 probabilities were entertained. And so we'll talk about those, and that's basically what we're going to say about it. So next time, new particle physics. It's going to start with the deuteron. Why is it 2 thumbs up? I don't know that we're going to get to that answer, but
It's just happy to be there.
what's that?
It's just happy to be there.
It's, you know, they're both, they see the world the same.